We're going to start our study of one-dimensional motion, and I'm going to start by jumping back and using an equation that you probably used in an algebra class, the old distance equals rate times time equation. Okay, so let's see how that might work. We're going to start getting more sophisticated with our notation very soon, but we'll start with this. A car turns on to Interstate 90 at milepost 179 in Moses Lake. 1 hour and 45 minutes later, the car exits Interstate 90 at milepost 182 in Spokane. Determine the average speed for the trip in miles per hour. Well, something we'll have to assume here is that those mileposts are actually correct distances between them. So, and by the way, it would exit at milepost 282 in Spokane, not milepost 182. Otherwise, this would be one long, slow, boring trip. So anyway, let's see how this works. In this case, we want to know the average speed. Well, that'll be the rate in this case. And if you do the algebra on that thing, you would just get rate is equal to distance divided by time. Now, we know how far the distance is. It's going to be 282 minus 179, which, doing that in my head, I think I get 103 miles. And I want to do a little bit of unit conversion here just to show you how to do it. But to determine the average trip in miles per hour, I know that 1 hour and 45 minutes happens to be an hour is 60 minutes. So this would be 60 plus 45, it'd be 105 minutes. Now, some of you may be looking at that and thinking, well, why didn't you just call it 1.75 hours? I could have, but if I do it this way, it'll give me a chance to demonstrate some unit conversion on here. Now, there's only one time when the letter M by itself is going to stand for miles. Nearly always in this class it'll stand for meters. But when you see the combination MPH, that's understood to mean miles per hour and not meters per hour. But anyway, let's go ahead and do the calculation on here. 103 miles over 105 minutes. Those are each probably good to 3 significant figures. So we'll just go with that. And I get about 0.9. Let's see, I need to show more significant figures on my calculator. And that's miles per minute. Okay, but that's not what I want. I want it in miles per hour. All right, so need to do a unit conversion. Now, the miles are just fine, but those minutes aren't so good. I have to have a unit conversion factor, something to multiply this by. Then it so happens that 60 minutes is equal to 1 hour. And so that's what I'll use. Now, I've got minutes on the bottom. I need to get rid of them, so they go on top. 60 minutes up here. And on the bottom, 1 hour. Okay, and when I multiply by that, the minutes will divide out. I'll end up with miles left and hours on the bottom. And so the rate of this car would equal, and I get about 58.9, again to 3 significant figures. MPH, and this is one of those times where that M stands for miles. Ordinarily it's meters. Okay, well, not so fast. Now let's suppose the person left at noon and arrived or took that exit in Spokane at exit 282 at 1:45 p.m. How fast were they going at 1 p.m.? You can't say from the information we have. All we know is when they left And when they got there, we don't know what happened in between. The reason for this slow speed might have been because they stopped in Ritzville for lunch. So you can't say anything about what's going on in between there. Let's try another one. A high school runner in training runs a 4.2 mile route in 26 minutes. Determine the runner's average speed in miles per hour and meters per second. This happened to be when I lived in West St. Paul going to high school. There was a 4.2 mile loop that I would run frequently, probably well more than 100 times. And I think 26 minutes was probably one of the better times that I ever did it in. So anyway, but that was long ago. I could not do that anymore. So let's figure out the rate here. I can use this same equation. Rate is distance divided by time. And it's going to be 4.2 miles on top. That's the distance. And 26 minutes on the bottom. I've only got two significant figures with each of these numbers, so that's all I'm going to keep. It looks like 0.16 miles per minute. Okay, so that's that part of it. Now, I need to convert that into miles per hour first, and so I can use the same thing I had up here, that 60 minutes is equal to 1 hour. I've got minutes on the bottom here. To get rid of them, I'll take the 60 minutes over 1 hour. Now, because those two things are equal, this is 1. Same thing up here. That's equal to 1. And it's a funny looking one. When I taught algebra, I'd call these conversion factors funny looking ones, but that's just what they are. They end up changing some of the variables that you've got in here. Some of the labels, the miles and the minutes and things like that. But this is just equal to 1. And when you multiply by 1, you get the same thing. It's an equal sign. So 0.16 times 60, and I get about 9.7 miles per hour. I'm going to go ahead and leave it that way because I've got another conversion to do here. So now let's figure out the speed in meters per second. 9.7 miles per hour. Whoops, I'm supposed to convert it into meters per second. This is going to be a two-step conversion or a two-factor conversion. The first thing I want to do is convert, well, doesn't matter which I convert first because multiplication can be done in either order, but I happen to know that 1 mile is equal to 1,609 meters. You can look that up. And 1 hour, well, there's 60 minutes in an hour, 60 seconds in every one of those minutes. There's actually 3,600 seconds in an hour. And if you do these conversions often enough, you're going to have that memorized. Anyway, it doesn't matter which one I multiply by first. I'll do the I've got an hour on the bottom. I'll put the 1 hour on top and 3,600 seconds on the bottom. And then I'll just keep the multiplication going here. I've got, let's see, I've got miles on top. I'm going to want miles on the bottom. 1,609 meters. And there. I only have one equal sign in this thing. Take care of the whole works all at once. So I've got the 9.7 there. I can multiply by 1,609 and divide by 3,600. And I get about 4.3 meters per second. And here's how the units work. Miles on the bottom here, divide with the miles up top there. This is all going to be one numerator. The bottom is going to have hours times 3,600 seconds times 1 mile. The hour on top here will divide with the hour down there. And my units left are meters on top and seconds on the bottom. So That's how I did it. I kept the units at every step of the calculation. That's a habit you should build. Sometimes you may, well, if we were doing this live in class where I can't edit things, when I was working on the whiteboard solving a problem, I'd get toward the end of a complicated problem a lot of times, and I'd start slowing down and looking ahead and thinking, ooh, am I going to end up with the right units? And because I keep units at every step, I often catch mistakes when I don't have the right units at the end of a problem, and it's time to back up and figure out where things went wrong. So keep units at every step in your calculations. Now, fancier notation. Instead of d's, we're going to use delta x, and that means x2 minus x1. In your textbook, they're using x1 minus x sub 0, x sub 1 minus x sub 0. It's still a delta x no matter what subscripts you put on these things. Then we'll talk about a time interval, delta t. That's t2 minus t1. And x1 is related to t1. It's the position at t1. x2 is the position at t2. Average speed. Now, they're using a, let's see. Oh, I know what they're doing. They're putting a bar over the top of the average. I tend to just call this VAVG. Okay, the bar can sometimes get misplaced, but if you see that AVG on there, you're not going to lose that. You know this is an average speed, or in this case, an average velocity it could be, which we'll talk about soon. Let's see. Okay, it's going to be delta x over delta t, okay, or x2 minus x1 over t2 minus t1. So that's something. In the book where they're using x sub 1 as the later time and x sub 0 as this, you could think of as average velocity, and we will do this sometimes, as x1 minus x sub 0 and t1 minus t sub 0. Often our t sub 0 is just going to be the time when time is 0, and so this thing will actually be 0, and the x sub 0 will be the position when the time is 0. Okay, this chart is position as a function of time for an object, and we're supposed to graph the position as a function of time. Okay, well, position, that's going to be x, and it's measured in meters. So the way you make a graph, label the axis, put the units that it's measured in. This x position is measured in meters. When you see something that says graph something as a function of, that means the thing before as a function of goes on the vertical axis. The thing after as a function of goes on the horizontal axis. We do a disservice in algebra classes when the only thing we ever have is y on a vertical axis and x on a horizontal axis, because in actual data you never have just y and x. You've got a vertical axis and a horizontal axis. Anyway, here's our t in seconds. Now we've got 10 seconds going here. This is my origin down here. I'm going to let it be 0 for both of my axes. This is 5 here and this is 10 here, so may as well use those for 1 square for each of these things. But the x position goes all the way up to 45. Well, I don't have 45 squares there, but if I let each one equal 5, each step equal 5, this would be 25 and this would be 50 up here, and I only have to go to 45, so that'll work well. So I'm just going to label these 2 points. This is 50, this is 25, and I don't have to fill them in between. I can figure those out. 5, 10, 15, 20, okay. You've done that. Now at time 0, that's right here, the position of the thing is at 5 meters, which would be right here. So this thing isn't starting at the origin, it's starting 5 meters to the positive x direction from that. At 1 second, it's at 9, which this would be 10 here, so it's going to be just a smidgen short of that. At 2 seconds, it's 13. So that's going to be, remember this is 10, this will be 15, so 13 would be about here. And I'm just going to fill in the rest of these points without describing what's going on. Okay, I've got all of the data points on there. Looks like a nice straight line here. Now, determine the average velocity for the interval from 0 seconds to 5 seconds. Okay. Now, here's the thing for this little interval here. I'm going to use their notation since we're going from 0 to 5. I'm going to use a notation where I'll say v average, oops, I'll switch back to black for this, is going to be, remember it's delta x over delta t. Well, I'm going to call the later time x sub 5, that's the position at 5 seconds, and the other one, x sub 0, the position at 0 seconds, and then down here I'll have the time at 5 seconds minus the time at 0 seconds. Okay, well at 5 seconds it's at 25 meters. I'm going to keep the units at every step in my calculation. At 0, it was at 5 meters. And the time that passed would be 5 seconds minus 0 seconds. That ends up being 25 minus 5 is 20, divided by 5 is 4. The average velocity in this interval is going to be 4 meters per second. Okay, so we've got an average velocity there. What about the average velocity for the interval from 3 seconds to 10 seconds? Well, I can write a new equation here. Delta x over delta t again. Variable-wise, I'd call it, this later time is 10 seconds, so I'd call it x sub 10 minus x sub 3. And that's just, that subscript is just a way of telling myself when that x position is measured. And the delta t will be the t at 10 seconds minus the t at 3 seconds. Okay, well at 10 seconds it's at 45 meters. At 3 seconds it was at 17 meters. T10, that'll be 10 seconds minus 3 seconds. This one, 45 minus 17, happens to be 28, I'm pretty sure. Check that if you don't trust me. 28 meters divided by 7 seconds, which is also 4 meters per second. All right, if you printed this off, you know that the next question is, how do the two velocities compare? Well, they look like they're equal. Can you tell by looking at the graph how they should compare? Okay, yes you can. And here's why. Delta x on this graph for this first interval ends up being the distance here. That is delta x for that first interval. Whoops. Yeah, goes right to there. Delta t for this first interval. So here's delta x. Delta t is this distance here on that horizontal axis, which is measured in seconds. That's delta t. Well, another way to describe delta x on this x versus t graph for this little interval This is the rise. This is the run. Okay. Rise over run. Maybe you remember this from an algebra class if they introduced it that way. That's the slope of the graph between these 2 points. And if you did the same thing for the 3 seconds to 10 second interval, you'd get a different rise and a different run, but it would be the slope of the graph from, let's see, 1, 2, 3, here up to here. Well, just looking at those points, you can see the slope of this line doesn't change. That's a big idea. The velocity, or the average velocity, AVE, between 2 points, this is going to be a mouthful, is the slope of the position versus time graph. Between those 2 points. Okay, that's a big idea. You can glance at a graph and see if you've got constant velocity, if it's a position versus time graph. If it's a nice straight line like this one is, it's got constant velocity. If it's not, if it does something weird, then it doesn't have constant velocity. Now, the last question here is a little bit scary. Write the equation of motion for the object. Well, you may have done something like this in math class where you always have y on the vertical axis and x on the horizontal axis. You probably remember this equation, y equals mx plus b, where x is the variable on the horizontal axis and y is the variable on the vertical axis, and m is the slope of the graph and b is the position at time 0. It's the y-intercept or the vertical intercept. Okay. Well, our graph isn't going to be y versus x. It's going to be x versus t, but we're still going to have a slope to it. M will have t, that's our horizontal axis variable, and our vertical intercept is going to be where the object is at time 0. That's x sub 0. Now, we're not going to call it m all the time. That's going to be our average velocity in this case. In fact, when we have constant velocity as we do here, this will be v average times t plus x naught. For reasons that are kind of lost in history, we usually write these in the opposite order. When you have constant velocity, here's the equation that describes your motion. It's x sub 0. Oh, by the way, x sub 0, physicists tend to call it x naught. And in Britain, if you were taking a math class or something, they'd refer to 0 as naught. So that may be why it showed up that way here. But anyway, it'd be plus v average times t. Now, if you have constant velocity, you don't need to call it v average anymore because it's the same all the time. And so you might just write this x equals x naught plus vt. And that's the way that you'd deal with the thing.